Hi everyone. Today let's gonna start sessions 5.3, the fundamental theorem of calculus. Big idea. Integration and differentiation are inverse process. That means antiderivatives can be used to compute definite integrals. Big skills. You should be able to calculate basic definite integrals by computing the difference of the antiderivative evaluated at the bounds of the integration. Okay, so first of all, let's look at area function. Let f be a continuous function for t greater or equal to a. The area function for f with the left endpoint a equals to, so here we draw the picture. Let's say this is our function f, let's say this is a, and then let's say this is the t s's, this is the y s's. Okay, let's call this guy be x. The area function of f with the left endpoint a is the area under the function f, and then bounded by t equals to a and t equals to x. So that's the integral of, this is the definite integral of a to x f of t dt, where the x is greater or equal to a. So after you evaluate this, and then you can see when x increases, the area also increases, right? So you can see here a is a function of x. And also notice that if your function is negative, then your area might be negative, okay? So this area function is a function of x. This area gives the net area of the region bounded by the graph of f and the t-s's on the interval from a to x. So last time we talked about the net area is the definite integral. The total area is the definite integral of the absolute values of f of t, okay? So that is the area function. Let's look at example 1. Consider the trapezoid bounded by the line f of t equals to 2t plus 3 and the t-s's from t equals 2 to t equals x. So let's draw the picture. So we have the t-s's and we have the y-s's. Okay, so the line 2t plus 3. Okay, I'm gonna make it longer. Okay, and I'm gonna move my t a little bit. Oops, it also moved my y. Okay, it's okay. Let me redraw the t. Okay. Alright, so then we can have more space. So this is t. This is 0. Okay, so 2t plus 3. When t equals to 0, we get 3. When t equals to 2, okay, when t equals to 2, 2 times 2 is 4. 4 plus 3 is 7. Okay, so it passed through these points and we connect them smoothly. We get a line, right? Okay, so we want to find the area. Okay, the area function, we want to find the area from 2 to x. Let's say this is x, then this guy is the area function a of x. Okay, so you can see this is actually the area of a trapezoid. Do you know the formula for the trapezoid? Okay, let me remind you. So for trapezoid, let's say this is A, this is B, and the height is H. Okay, how do we calculate the area of trapezoid? Well, you have another copy of it, and then you flip it down. So then this is B, this is A. So what do you get? You get a parallelogram. So a trapezoid is half of a parallelogram. The parallelogram, the base is A plus B and the height is H. Okay, so this is the area of the trapezoid. So far, so good? Okay, so now let's work on the problem. Okay, so part A. Evaluate A of 5. Well, what is A of 5? So that means we're looking at when x is 5. So this is 5. Okay, so this guy is A of 5. Okay, so using the formula, we want to have 1/2. Okay, what is the top of the what is the A of the trapezoid? So we have the formula is 1/2 A plus B times H. So A, well, let's use how about purple color? Okay, so my A is 7, right? How about this guy? Well, we plug in 5 into the function. So f of 5 is 2 times 5. So this f of 5 is 2 times 5 plus 3, which is 13. So 1/2 A is 7, B is 13 times height. My height is, what's the difference between 5 and 2? That's 3, right? So 7 plus 13 is 20. 20 divided by 2, 10. So that's 30. 30 is A of 5. Okay? So that's part A. How about part B? Alright, so part B, we want to find the area function A of x. Well, that's 1/2. A is 7. B is what? Well, you look at this guy. B is actually f of x, right? Times the height. The height is x minus 2. What is f of x? Well, f of t is 2t plus 3. So f of x is 2x plus 3 times x minus 2. Okay, now let's see. 7 plus 3 is 10. Oh, you see? We can factor out the 2 and then cancel with the 2 in the denominator. When we factor out the 2, we get x, and then 10 becomes 5. Let's multiply out. So when we multiply out, we get x squared, and then minus 2x plus 5x, minus 2 times 5, 10. So which is x squared plus 3x minus 10. Okay, so that's part B. Part C, we want to compare the derivative of A to f. What's the derivative of A? Derivative of x squared is 2x. Derivative of 3x is 3. Derivative of constant 10 is 0. Oh, compared this guy to f of t. Well, f of t is 2t plus 3. So 2x plus 3 is actually f of x. Wow. The derivative of the area function is actually f when we plug in x. Okay, everybody? Does this work for all the functions or just this line? Actually, it works for all the functions. Okay, so this is actually true for all the function. The derivative of the area function equals to the functions evaluated at x when we plug in x. Okay? Alright, so here is the fundamental theorem of calculus, part 1. Okay, let me change the color. If f is continuous on the interval ab, then the area function a of x is the definite integral from a to x of f of t dt. Okay, so you can see the picture. This is the area function, the orange area. Okay, and you can see the area function is continuous on AB and differentiable on AB. The area function satisfies that derivative of A equals to f evaluated at x. Okay, so i.e. the derivative of A with respect to x is the dx of the definite integral from A to x f of t dt. Well, that equals to f of x. So there are two things I want to emphasize. Okay, the first thing I want to emphasize is you can see this lower bound or lower limit of integration is constant. Okay, that's the first thing I want to point it out. The second thing is you see this x, they have to be the same. Okay, so once it satisfies those two conditions, then the derivative and the antiderivative cancel out. You just plug in the upper limits. Okay, so you plug in the upper limits into the f. Okay, so which means the area function of f is an antiderivative of f. Okay, so how do we show the fundamental theorem of calculus? Well, here, I'm gonna give you some idea. So, we know this orange area is a of x. Now, let's consider x plus h. Well, here, this is x plus h, where h is a very tiny number. Okay? Then, well, you realize this green area is a of x plus h. Do you agree? Then when we subtract them, what do we get? So when we subtract them, this little strip is actually a of x plus h minus a of x. Right? It's the green area minus the orange-yellow area. Okay? It's this thin area. Okay? So that is a times a of x plus h minus a of x. Okay? Can you see this guy is actually very close to the area of this rectangle? Okay? Can you see it's very close to the area of the rectangle? What's the area of the rectangle? Well, the width is h, okay? How about the height? I can use one of the endpoints as my height, so I can either use f of x or I can use f of x plus h. Let's use f of x. We use the left endpoint. Okay, so what does that mean? Well, it tells us that a of x plus h minus a of x is approximately by h times f of x. And you can see when h is getting smaller, the area can be approximated by the area of that rectangle. So let's divide it by h on both sides. Now we see when we let h goes to 0, we get equal, right? When we take the limit, h goes to 0. This guy is actually equals f of x. But do you remember what's this guy? This is exactly the definition of derivative from chapter 3, right? The definition of the derivative is the limit. H goes to 0. A of x plus h minus a of x over h. So we have shown that the derivative of the area function equals to f of x. That is the fundamental theorem of calculus part 1. Okay, it talks about that the area function is an antiderivative of f. Okay, so how about part 2? So what does part 2 tell us? So fundamental theorem of calculus part 2 says that if a function f is continuous on the interval, closed interval ab, and capital F is any antiderivative of small f, then the definite integral of f of t dt, the definite integral of f of t dt equals to the antiderivative of f when we plug in b minus the antiderivative of f when we plug in a. So how do we prove that? Well, we know that the area function is an antiderivative. Okay, so suppose that f is another antiderivative. Then we have two antiderivatives. What's the relationship between two antiderivatives? They differ by constants. So we know that the capital F is like the area function plus a constant, right? And then so that's why f of a, b, f of t dt. This is like this is like the area function where when we plug in b in it. So far, so good? So what is a of b? Well, a of b is then, so from here we get, look, I don't have enough space. So let me create more space here. Okay. All right. So here we get a of x is f of x minus c, right? So a of b is then f of b minus c. But what is c? Well, let's plug in a. Okay, let's plug in a here. So a of a is f of a minus c. But what is a of a? Well, a of a is the integral from a to a f of t dt. We know by definition this is like a line segment. What's the area of a line segment? Is 0. So that tells us that f of a equals to c. That's why we plug in here. We get that equals to f of b minus f of a. Okay. So that's why given any antiderivative, the definite integral of f of t dt from a to b equals to the antiderivative. We plug in the upper limits of integration b minus the antiderivative. We plug in the lower limits of integration a. Okay, so that's the fundamental theorem of calculus part 2. Now let's see how we use those theorems to work on our examples. Okay, so example 2. Find the derivative of g of x equals to x, definite integral from -1 to x e to the t squared dt. So by the way, we are not able to integrate. We are not able to integrate e to the t squared dt. We're not able to integrate. So not able to integrate. Okay, so you cannot like integrate this guy and then you find the antiderivative and then plug in x minus plug in -1. We're not able to do that. However, we can use the fundamental theorem of calculus part 1. So what is the derivative? Well, that's the derivative of g of x is -1 to x e to the t squared dt. Okay, so let's check the two conditions of fundamental theorem of calculus part 1. So what are those? First, we want to check whether the lower limit of integration is a constant. Second, we want to check whether the upper limits of integration x and then with the derivative with respect to x, are they the same? Okay, let's check that. So here, let's make it so colorful. Okay, so is the lower limits of integration constant? Yes. Is this guy and this guy the same? Yes. Then by the fundamental theorem of calculus part 1, it tells us that this guy, the derivative of the antiderivative, they sort of cancel out, and then the result is just the function itself. We're not integrating, we're not differentiating the function itself. We place t by the upper limit of integration, which is x. So we get e to the x squared. So far, so good. Here, we're not integrating e to the t squared. We're not differentiating e to the t squared. We just simply replace t by x. Okay, that's the easiest case. Let's look at example 3. Okay, so the derivative is d dx integral minus 1 to x squared e to the t squared dt. Okay, so let's check. Is the lower limit a constant? Yes. Next, what do we check next? Is the upper limit the same as this guy? Oh no! What do we do? If they're not the same, we gotta make it the same. So how do we make it the same? First of all, can we change this guy? No, this is the problem. We cannot change that. We cannot change that. Can we change this guy? Yes. By chain rule. Okay. So let me write it down here. Okay, so let me create more space here. Okay, let's do that. Okay, so here, by chain rule, what is chain rule? Chain rule tells us that dy dx is dy du times du dx. So you can kind of replace it by u, but you just multiply by du then, okay? So in this case, our u is like x squared. I want to create the x squared here. So this is like our u. Okay, and then we have the y. This is the y integral from minus 1 to x squared e to the t squared dt times du dx. U is x dx squared, so dx. See, we're using chain rule. Let me see. So this is like y dy du times du dx. That's the chain rule. Okay, now what happened? Well, what happened is, now you can see the lower limit is a constant. Yeah. And then you can see the upper limits there. It match with the x squared in front of it. So they match. Okay, so we can use the fundamental Theorem of Calculus Part 1. Okay, that part is our function. We're not differentiating, we're not integrating. It's the same function, but we just replace t by the upper limit. But the upper limit is x squared. So that's why t squared. That is the first term, okay? That is the first term. How about the second term? We still have this guy is the derivative of x squared is 2x. Okay, so that's why our final answer is e to the x to the 4th times 2x. Okay, so this is what we're gonna do. If the lower limit is a constant, that's good. If the upper limit does not match with the dx in front of it, we need to use chain rule. Okay, so we match whatever u there, and then we multiply by du dx. Okay, so once they're matched, we can use fundamental theorem of calculus part 1. We place t by the upper limit. Okay, and don't forget the chain rule, the u prime, multiply by u prime at the end. Okay, so that is example 3. Okay, so how about example 4? Okay, so you can pause the video and try to work on this problem on your own. Okay? Are you done? Yes? Let's go over it together. So g prime of x equals derivative of 1 to sine x key root of ln of t plus 4 cosine t dt. Okay. First of all, let's check. Is the lower limit constant? Yes. Are these the same? Oops, no. Then what do we do? What do we do if they're not the same? We need to use chain rule. What do we want to match there? So because this is sine x, we want to match. We want to make it the same, but we cannot change this problem. We cannot change this part. So the only thing we can change is this guy, okay, in front of it. Okay, so let's copy down here. Key root of ln of t plus 4 cosine t dt. And because we're using chain rule, we have d sine x dx. All right, everybody. Okay, so let's continue. Now we can see the lower limit is constant and the upper limit. So this is constant and the upper limits match with the guy in front of it. So we can use the fundamental theorem of calculus part 1. So that is the same function. Okay, we're not differentiating, we're not integrating it. We replace t by the upper limit, which is sine x. So we place t by sine x. Okay, so that's the first factor. Okay, that's this guy. And then we still need to multiply by u prime. What is u prime? U prime derivative of sine x is cosine x. So this is the u prime. So far so good, everybody? Okay, let's slowly increase our difficulty. Now let's look at example 5. Okay. So we want to find the derivative of g of x. So g of x is the integral from x to the 4th to 1 e to the t secant t plus 3t squared. Okay, so let's see. G prime is d dx integral from x to the 4th 1 e to the t. By the way, we're not able to integrate this function because it's more complicated. We only know the basic formula. Okay, if the antiderivative are those form, we're able to integrate. If they're not those form, then we cannot do it. So for a derivative given any function, we can always find the derivative either by like combination of product rule, quotient rule, and chain rule. But for integrals, this is not true. Given a function, we cannot. So I would say most of the integrals we're not able to solve and get a nice formula. Okay, we're very limited. We can only integrate some part of it, some part of the functions. Okay, which is like the formulas I give you. So even though we go to calculus 2, we will talk about more integration techniques such as like U substitution, integration by parts, trig substitution, partial fraction, but those can only help us to integrate like more functions. We're still not able to integrate all functions. Okay? All right, so let's continue with this problem. First, is the lower limit of a constant? Oops, no, the constant is actually upstairs. What do? How do you make it downstairs? Well, we flip them, right? Can we just flip it? No, we cannot just flip it. When we flip it, what happened? We gain a minus sign in front. Okay, so we flip it, but we gain a minus sign in front. Now, what happened? So now the I use square to denote. So now the lower limit is a constant. Good. But the upper limits, are they the same? No. So what do we need to do? we're gonna do chain rule. So chain rule, what do we want to match here? We want to have x to the 4 there. Okay, so if we put x to the 4 there, we also need u prime dx to the 4th dx. That's the chain rule. Now, because we have the lower limit is a constant, the upper limit match the guy in front of us, we can use fundamental theorem of calculus part 1. That is, is the function we replace t by the upper limits of integration. T squared, so x to the 4 squared is actually x to the 8. We multiply the exponents. Okay, and then times, what's the derivative of x to the 4th? Well, 4x cubed. So far, so good, everybody? Okay, let's increase the difficulty. What happens if our g of x looks like that? Well, what do? We want to differentiate that guy. So sine x, cosine x, ln of e to the 5t minus sine of 3t dt. Okay, so let's check. Is the lower limits of integration a constant? No, neither the top one nor the bottom one are as constants, right? So what do? Okay, do you remember if we want to integrate the area from A to B, we can cut it in C. We can integrate this piece first and then integrate this piece, then we can add them together. So the C is any number we choose. So here we can choose C to be a constant. What constants is the easiest number? We can choose 0. Actually, any constants works, okay? You can choose any constant here, but I love 0, okay? So let's split. So we split, then it becomes sine x to 0 of our function. This is t. Yes. Remember, the function inside is a function of t. And then we have 0 to cosine x, ln of e to the 5t minus sine 3t. Okay, dt. Alright, so, but also you realize, oh, that's not enough because this guy, my constant is on the top. What do we do to bring it down? So, what do? We actually can flip it by putting a minus sign in front of it. Then we get an integral from 0 sine x derivative ln e to the 5x minus sine 3 t. So be careful. Yes, sometimes I copy the wrong thing. So we need to double check it before we continue. So d dx of 0 cosine x ln of here as well e to the 5t. I pressed something wrong. Minus sine 3t dt. Okay, so now we can see all the lower limits of integrations are constants. Okay, but how about the upper limit of integration? Are they the same? No. So we're gonna need chain rule. So this is the hardest problem it can be of this type of problem, like using the fundamental theorem of calculus part 1 to find the derivative of functions that is defined by a definite integral. Okay, so let's get a chain rule. We need to have sine x don't forget u prime. So d sine x dx. The second one, we want to have cosine x at the bottom so that we can match the cosine x here. and u prime. So d cosine x dx. Okay, so what is that? Okay, so well, once we have the lower limit as a constant and the upper limit match with the guy in front of it. Oh, do I miss the d here? Yeah, I do. Okay. Okay, so by fundamental theorem of calculus part 1, the first guy, what's the first guy? So this is we replace t, so it's a function. We replace t by the upper limit, which is sine x. So sine of 3, t is sine x. It's okay. We can have sine of sine, right? And close the parentheses. And then derivative of sine x, what is that? That is derivative of sine is cosine x. Okay, and then continue. Here we have fundamental theorem calculus, so that's the same function. We replace t by upper limits cosine x. 3t, t is cosine x. So here it's better to write the parentheses. Otherwise, if you don't write the parentheses, what does it look like? It looks like sine 3 times cosine x. It's not like sine of 3 times cosine x. So this parentheses is very, very important. And this parentheses take care of this one. Okay? And then the last one, derivative of cosine is minus sine x. And this is our final answer. And you can just leave it like that. You don't need to simplify. So far, so good, everybody. So these are the problems using the fundamental theorem of calculus part 1. Okay, so you have functions defined by a definite integral, and we want to find the derivative of that functions. So derivative and antiderivative sort of cancel, but sometimes when you use the theorem, you need to make sure 2 conditions. First, the lower limits of integration is constant. Okay, and the second condition is the upper limit of integration match with the derivative in front of it. So you take the derivative with respect to the same guy. So that's why if your lower limit is not constant, you check whether the upper limit is a constant. If yes, then you can flip it, but you will get a minus sign in front of it. If both of the limits of integration are not constant, you can like cut it into half. Okay, like this example, you insert a constant 0 so you split the integral into half and compute that. Okay, and to make the upper limits of integration match with the guy in front of it, we use chain rule. Okay, so don't forget to multiply by u prime at the end. Okay, so that is the first part of this session. So we'll continue in the next video.